Welcome to Chapter 15. We will begin by talking about electron dot structures and the formation of ions. So the first thing we need to talk about are valence electrons. These are the electrons located in the shell that is furthest from the nucleus. These are the electrons that participate in chemical bonding. So the number of valence electrons for most elements is 1 for the elements of group 1, 2 for the elements of group 2, 3 for the elements in group 13, 4 for the elements in group 14, 5 for the elements in group 15, 6 for the elements in group 16, 7 for the elements in group 17, and 8 for the elements in group 18. These valence electrons are represented by dots next to this symbol for the element. So you'll notice here, group 1, we have hydrogen, lithium, sodium, potassium, rubidium, cesium. They all have 1 dot by them. And your noble gases have 8 around them, with the exception of helium, which in its filled valence only has 2 electrons. It's kind of an exception to the rule there. The single dots are likely to form bonds with other elements because the electrons like to be formed as pairs in a bond so that you're sharing 2 electrons between the nuclei of 2 different elements. These paired dots are called non-bonding pairs. Those paired ones that you find around an element usually don't form bonds. They usually stay as they are. There's a couple of exceptions where you'll form double or triple bonds and use them, but usually they don't. And so those are your non-bonding pairs. So let me give you an example. If you look at nitrogen under 15, it's the capital N, you'll notice it has 1 pair and 3 single dots. So nitrogen generally has a non-bonding pair when it bonds, and then it bonds 3 different places to another element. So for example, if nitrogen were combining with chlorine, it would most often have the nitrogen with 3 chlorines that have all contributed their 1 single dot to form a pair where the nitrogen has single dots, and you'd get NCl3. Ions occur when you take the number of electrons that the neutral atom has, where the protons and the electrons are matching, and you remove or you add to the number of electrons that are there when they match. So now you'll have more electrons than protons or fewer electrons than protons. So elements by themselves, if you were to add up the plus charges, which is what protons have, and the negative charges, which are what electrons have, they would add to give you 0. But when you have an ion, they no longer add to give you 0. You get a positive charge or a negative charge, depending on whether you have more protons or more electrons. Now the protons aren't going to change, but the electrons can go up and down. So if you remove 1 electron, then you'll end up with an extra proton to the number of electrons, and you'll have a positive charge. That's kind of counterintuitive because it goes opposite of our bank accounts. Usually when we remove something, we think of having negative money in the bank account, but with an atom, when you're making it into an ion, when you remove an electron, you end up with a positive amount because you're removing the negative amounts. If you add an extra electron, then you're adding a negative charge, so now you're going to end up with a negative charge on that ion because the proton number remained the same, but the electron went up, so you've increased your negative charge. When metals bond to nonmetals, they often form ions. The metal will form a cation, which means it will be positively charged. It will give away its electrons. And the nonmetal will form an anion, which means it will be negatively charged. It will take those electrons and end up with this excess of negative. The metals donate because they have very few valence electrons. And ideally, all the elements want to have the same number of electrons as a noble gas, because noble gases are our most stable way of having electrons. And so, if they're in group 1, they have 1 valence electron, they will donate that 1 electron, and they'll tend to be +1 charged when they're in a compound. If they're in group 2, they have 2 valence electrons, so I'm guessing you could probably guess they become +2 for their charge. And the group 3 metals, aluminum is the most common, will become +3 charged. And this gives the elements the same number of electrons as the noble gas in the prior row of the periodic table. So the nonmetals will usually accept electrons when they're combined with metals because they are closest to getting to the noble gas electron configuration by adding electrons in, because they've got more than they're missing. So your group 17, fluorine and down, are going to take 1 electron and scoot to the right electron-wise. But remember, their protons stay the same, so the identity of the element doesn't change, just its electron setup changes. Your group 16 will usually become 2- because they're going to take 2 electrons to get up to that 18. And the group 15 will usually become 3-. And so they take however many they need to get to the same number of electrons as a noble gas, that last row on your periodic table. You can also have elements that are combined into a molecule, and that molecule can have a charge. And when that happens, they call it a polyatomic ion. So, for example, you can have an oxygen with 1 hydrogen on it, and it will have a -1 charge, and that's called hydroxide ion, and that's involved in our bases. Or you can have 1 nitrogen with 4 hydrogens and a +1 charge for the overall molecule, and that's called an ammonium ion. And that's the one example of where you'll have a cation that acts like a metal but actually has no metals in it. So you can have like ammonium chloride or things like that. Even though there's strictly no metal in that ammonium, it acts like it, and so you'd end up with an ionic compound. So that's kind of an exception to the rule.